In this video, we'll solve our first linear system with infinitely many solutions using a Gaussian elimination. We'll do that in example 3.2.12. We want to solve this linear system using a Gaussian elimination. The first step of Gaussian elimination is to write the augmented matrix of the linear system. So we have -1, 3, -3, 4, 0 in our first row, -2, 9, -3, 2, 3 in the second row, -1, 3, -3, 6, 8 in the third row, 1, -1, 5, -8, 2 in the fourth row. That's our initial augmented matrix. This augmented matrix is not in row echelon form. The next step is to transform it into an augmented matrix that is in row echelon form using elementary row operations. Now, which elementary row operations should we use? What should we start with? Let's start by clearing all of these entries. We want zeros in all of those positions. Now we need to find elementary row operations that will help us achieve this. For the second row, row 2, -2, row 1, we'll make that -2 become a 0. Then for the third row, row 3 minus row 1, we'll make that -1 become a 0. And then row 4 plus row 1, we'll make that 1 become a 0. So the first row isn't changing, -1, 3, -3, 4, 0. The second row is changing, so we have -2, -2 times -1, so that's -2 plus 2, that's 0. Then we have 9 -2 times 3, that's 9 minus 6, which is 3. Then we have -3 -2 times -3, so that's -3 plus 6, which is 3. 2 minus 2 times 4, that's 2 minus 8, which is -6. 3 minus 2 times 0 is 3. That's our new second row. Then in the third row, we'll have a new first entry. It will be -1 minus -1, so -1 plus 1, that's 0. That's great, we want that 0 there. Then we have 3 minus 3, that's also 0. -3 minus -3, that is also 0. 6 minus 4, that's 2. And 8 minus 0, that's 8. In the fourth row, we have 1 plus -1, that's 0. That's good, we want that 0 there. -1 plus 3 then gives me 2. 5 plus -3, that's 2. -8 plus 4, that's -4. 2 plus 0, that's 2. Alright, I am making progress, but my matrix is not yet in row echelon form. What I can notice now is that the second row and the fourth row looks like they're multiples of each other. And so I know that if I perform a couple of row operations there, I'm going to get a row of zeros. And so the first thing I'll do is I will perform the elementary row operation 1 over 3 times row 2. And then I'll be able to use row 2 to clear row 4. So my first row stays the same, -1, 3, -3, 4, 0. The second row is now 0, 1, 1, -2, 1. The third row stays the same, 0, 0, 0, 2, 8. And the fourth row is still 0, 2, 2, -4, 2. Now I can use the second row to clear the fourth row. Row 4 -2, row 2 will be the elementary row operation that achieves that. So in the first row, I still have -1, 3, -3, 4, 0. In the second row, Still have 0, 1, 1, minus 2, 1. Third row, 0, 0, 0, 2, 8. The only row that's changing here is the fourth row. So 0 minus 2 times 0 is 0. 2 minus 2 times 1 is 0. 2 minus 2 times 1 is 0. Minus 4 minus 2 times minus 2. That's minus 4 plus 4. That's also 0. And 2 minus 2 times 1, that's 0. Now this augmented matrix is in row echelon form. I have a row of zeros, but it's at the bottom of the augmented matrix. Also, the leading entries are all to the right of the leading entries of the rows above them. Now the next step is to find the corresponding linear system. So I have minus x1 plus 3x2 minus 3x3 plus 4x4 equals 0 as my first equation. Then I have x2 plus x3 minus 2x4 equals 1 as the second equation. And the third equation gives me 2x4 equals 8. The fourth equation gives me 0 equals 0. I will not write that one down. Next, I will identify the leading variables and the free variables. The leading variables are the variables whose corresponding columns contain a leading entry. And so there are three of those, x1, x2, and x4. And that means that there's one free variable, x3. And that free variable we will set equal to t, a parameter. x3 is equal to t, where t is any real number. Next, we will replace all instances of x3 by t. So we have a new system of linear equations where x3 is replaced by t. So x1 minus x1 plus 3x2 minus 3t plus 4x4 equals 0. We replaced x3 by t. We'll do the same in the next equation. x2 plus t minus 2x4 equals 1, and 2x4 equals 8. This is our new system of linear equations. And this system we will now solve using back substitution. We have three equations, 1, 2, 3. We'll start with equation 3. 2x4 equals 8. That means that x4 is equal to 4. We've successfully solved for x4. We move on to equation 2. We have x2 plus t minus 2x4 equals 1. We now know that x4 is equal to 4, so x2 plus t minus 2 times 4 equals 1. And so x2 is equal to 9 minus t. Moving on to equation 1, minus x1 plus 3x2 minus 3t plus 4x4 equals 0. We now know both x2 and x4, so we can plug those in. So minus x1 plus 3 times x2, which is 9 minus t, minus 3t plus 4 times x4, which is 4, equals 0. Let's solve for x1. To solve for x1, I'll send x1 to the other side of the equation. So x1 is equal to 27 minus 3t plus 16. And so x1 is equal to 27 plus 16 is 43 minus 6t. So we've solved for x1, x2, and x4, and we set x3 to be equal to t. Let's write out the solution in parametric form and vector form. So in parametric form, we have that x1 is equal to 43 minus 6t, x2 is equal to 9 minus t, x3 is equal to t, and x4 is equal to 4. And that's for any t in R. And in vector form, we have x1, x2, x3, x4 equals, let's gather all of the constant terms into the first vector. So we have 43, 9, 0, and 4. And let's gather all of the coefficients of t in the next vector. So plus t times minus 6, minus 1, 1, and 0. It's for any t in R. For any value of t that I choose, I will find a new solution of the linear system. This system has infinitely many solutions. It is therefore consistent. Now let's find one solution of the system. Let's pick a value of t. Let's set t to be equal to 1. Then what do we get? x1, x2, x3, x4 will then be equal to 43 minus 6, that's 37. 9 minus 1, that's 8. 1 and 4. This is one particular solution of the system. If I plug in these values of x1, x2, x3, and x4 into the linear system of equations, I will find that every single equation is satisfied by these numbers. This is one of the infinitely many solutions of the linear system.